we have been working on exploring projective geometry, and one of the things we've discovered, and this is not novel, but they connect to regular polytopes in a number of interesting ways. So projective geometry involve these incidence structures. There are points and lines. Points are intersections of lines. Lines intersect at points. And there's this duality in the projective planes. Every pair of coplanar lines meets at a point. This duality is pretty significant part of some games. If you've ever seen Spot It, that's based on a order 7 projective geometry plane. So one interesting thing is that the lines through the origin in the higher dimension actually correspond to the points in the projective plane. So you can think of the points on the projective plane as being isomorphic to antipodal points on a sphere. So the phanoplane is the simplest projective plane. It's order 2 in 2 dimensions. It involves 7 points, 7 lines. But in this typical diagram, one of these lines is a circle, which kind of stands out a little bit. And in fact, the reason for this is the structure of the phanoplane consists of 168 symmetries, where the triangle doesn't have so many, and so some of the symmetry is actually hidden. So one way you can actually look at this is turning it into a tetrahedron instead. So instead of having the point in the middle of the triangle, we restrict ourselves to just the surface of a tetrahedron. And these points are colored in the same way. We have 7 pairs of antipodal points, 3 opposite pairs of edges, which are denoted with the dotted lines, and then 4 opposite vertices and faces. And they form they're in 7 lines. So the lines of the tetrahedron correspond to the lines in the phanoplane. This can actually be extended to higher dimensions, and in fact this is a model that Christian built that is actually the third dimension projective phanotetrahedron. It does use the interior, so it's more of this model than this model. And this extends to higher dimensions. So the projective geometry n, 2 as a regular n plus 1 simplex. So there are 2 to the n plus 1 minus 1 points for each of those projective spaces, and they correspond to antipodal pairs of surface facets on the n plus 1 simplex. So the only exclusions are the interior of the shape. And they all form these lines. So every pair of points connected by a line on the surface passing through a third facet. Now, if we go up an order into the projective geometry 2, 3, it corresponds to the cube. Points can be expressed as balanced ternary homogeneous coordinates. So we have 3 points that correspond with the form of having a single 1 and 2 zeros, and they correspond to the faces. And if you think of a cube centered on the origin, going from -1 to +1, they would be the -1 face and the +1 in each of the 3 dimensions. There are 6 points that have a plus or minus 1 and then a following 1. Those represent the edges, and then the 4 points that correspond to the vertices. And here on the picture we have the 13 points that shows where they would be arranged, as well as their shadow versions that are through through the poles. And there are 13 lines corresponding to the planes by just taking any pair of points again. So this property extends to higher dimensions. So this is a model of the PG3,3 as a hypercube, and Christian spent about a week highlighting all of the points and labeling them with different colored little pom-poms, and all of the spread of lines are done up in these silver pipe cleaners. And this extends to higher dimensions as well. And the lines are always planes through the origin, so you can find them fairly easily. Now, if we go up to PG2,5, there's a mapping to the regular dodecahedron. Unfortunately, it doesn't map quite as nicely. So we have 31 points corresponding to the facets of the regular dodecahedron, 6 pairs of faces, 15 pairs of edges, 10 pairs of vertices. But lines, you have to get a little creative. So for face-centered lines, everything works out fine. You've got 5 of those. But the 6th one, you end up with 5 edges around the equator and then a point through the pole. And then it gets really nasty when you look at some of the vertices and you have some weird situations. But unfortunately, the higher dimensions don't continue, and that's about as far as you can get. PG2,4, which I kind of skipped over, also has a mapping to the dodecahedron, although it's a little messy, and so we end up with you have to skip over the edges. So this was covered in a geometrical picture book, as well as Steiner systems from the projective plane. So what can you do with this? Well, we designed some card games based on projective geometry, and using the model helped figure out ways of representing that geometry. So come on up to the exhibition room and you can see our examples.